What is maximum likelihood estimation? So those of you that took my item response theory class, you've already heard me talk about this a little bit, but it's a different way of, and it's a common estimator. It's using a lot of different stats, using a lot of different more advanced statistical stuff for sure. Multi-level modeling it's used in, SEM, item response theory, all of it uses maximum likelihood. And it's got some favorable properties. There's a reason people use it, right? Because it can be a good, favorable properties that it's got. So what we're going to do today is to use maximum likelihood to estimate the mean of a sample. So we all know how to get a mean from a sample. You just average everything together, right? You just add everything up, divide by the number of things there, and that's your average or mean. We're going to try it using maximum likelihood today, so you can actually see how maximum likelihood works, what's being maximized, and what the likelihood is, what we mean by that. In general, what maximum likelihood estimation tries to do is to say, what are the population properties that were most likely to have generated data that look like this, right? So maximum likelihood estimation assumes that you've got data pulled for some population, and it assumes that the data are representative of that population. And what it tries to say is what properties of the population were most likely to have given rise to these kind of data, right? So the analogy I like to use is one familiar with. You go to a doctor, a physician, and you present a bunch of symptoms, right? You say like, I got a sore throat, I got a fever, I've got chills, what have you. And you present these symptoms, okay? The symptoms are like the observed data. This is what the physician has to work with. This is the observed data that the physician looks at. And what he or she's trying to do is to infer what illness is most likely to have given rise to these symptoms, right? So if the doctor knows, let's say that tuberculosis, is associated with fever, congestion, coughing up blood, right? And you're presenting with, I don't know, irritable bowel or something, right? Like they're going to know that's a bad fit, right? That's not very likely. Tuberculosis is not very likely to have generated whatever gastrointestinal ill problems you've got. So, so that's essentially what they're trying to do. They're trying to figure out what illness, what latent illness that they can't observe directly actually may have generated the symptoms that they can't observe directly. And that's what maximum likelihood does. It says, given the data I've got here, what was most likely to have generated it, right? And then it compares a bunch of different stuff. Just like a physician would in their mind compare, like, okay, these are 4 or 5 illnesses it could be, which one best matches the symptoms? Which one's most likely to have given rise to these symptoms? So that's the analogy I like to use. The difference, of course, is that the illnesses are like discrete categorical things, and usually we're trying to estimate something that's more on a continuum or whatever, but that's kind of what it's like. So, all right, everybody clear on kind of what I'm trying to say here, what we're trying to do? Okay, so what we're going to do, we're going to simulate a bunch of data in Excel, right? We're going to know the true population properties of that data. We're going to simulate one sample. We're going to do a big sample, like 500. And we're going to compute the mean and standard deviation of the sample like the normal way. And then we're going to try it a different way. We're going to use maximum likelihood estimation to try to figure out what population properties were most likely to have generated the 500 cases we see. Okay, so that's the steps. We're going to specify the shape of the distribution. We're going to make it a normal distribution. We're going to specify the mean and the distribution and the variance or standard deviation, right? And then what we're going to do is we're going to take each data point and evaluate the probability of witnessing that particular data point given the population properties. Then we're going to compute the likelihood by multiplying across those probabilities, and then we're going to try it a few times. So let's just get into it. I think it'll make more sense once I do that. Okay, so the first thing you need to know is that the function for the normal distribution is ugly, right? Now, everybody here is completely used to looking at normal distributions all day long. We work with them constantly. Very rarely do we have to see this ugly formula with a normal distribution. So it looks like this. It can also be written this way. These two are equivalent, right? This has got a 1/2, and here the 2's in the bottom. The 1's omitted, but it's up there. Right, the E instead of the exponent, but these are the same formulas here, right? Here it's a standard deviation multiplied outside the bracket. Here it's the square root of the variance. Same thing. So these two are the same formula here, where pi is, of course, 3.14, and the exponent is like 2.7, whatever. These are like properties of like math, right? Anyway, this is really, really unfortunate that this is so confusing and weird. But that is the formula for the normal distribution. And we're going to assume that our data are normally distributed, and in fact, we're going to simulate it to be so. And so I want to show you, first off, just that this is, in fact, the formula for a normal distribution, right? So this first tab I've got here, what I did is I just tried to build this formula. And I specified just a bunch of numbers going from 30 up to 70, right? And then I just started doing math. I just started computing this. So this part is I started from the inside out. So this is the y minus mu. So first thing I needed to do, I did need to give it mu and sigma. So mu is my mean I want this thing to have. And I made a mean of 50 and standard deviation of 5, okay? So this is just 30 minus the 50, which is this y minus mu, squared. That's all you see here in this column, right? And then over here is the rest of it. This is the negative 1/2 times this thing I just computed, which is y minus mu squared, right? Divided by the variance squared, right? Which is right here in this last part, okay? And then I just took the exponent of that. Okay. And then what I did is I did the first part of the equation. So if you look at this column, it's everything from here to the right. And then I just built the equation. This way I did 1 over the square root of quantity of 2 times pi, which I just manually put in as 3.147, times that standard deviation squared, right? Times all this other mess I computed. So anyway, I did that, and then I graphed it out. I just made a plot of all these numbers here, and you can see, sure enough, it looks like the normal distribution. Okay. So this is the formula, and this is the, we can think about this as a frequency distribution, right? The normal distribution is a frequency distribution. What it's saying is whatever it is we're looking at, we expect to be normally distributed around a given mean, where most of the cases are around the mean, and then fewer and fewer people or fewer and fewer cases occur near the tails, right? It's a frequency, the frequency with which we expect to see stuff occur. We expect a lot of values of 50, we expect very few values of 30, right? This is a frequency distribution. So the first thing you need to understand is the relationship between frequency and probability, right? So if something occurs more often in practice, like if we observe something occurring in a distribution that looks like this, we can make the inference then, if we go and observe more stuff in the future, the likelihood of seeing different values of X will look like this too, right? So if we have 500 cases or whatever, and we see most of them piled up in the middle, then we know that in the future, we're pretty likely to see 48s, 50s, 51, 52, right, on down the line here. And we know that based on this distribution here, right? And so there's a clear connection between frequency and probability. The more often we see things, the more likely we are to see those same things in the future, right? Does that, first off, that inferential leap make sense to everybody? Okay, good deal. All right. So what this formula is this is not a frequency distribution that I've computed here, right? What I've done is I've just actually said, just make one data point of each of these things and compute using this formula what this density looks like. Density is like, just means like how big it is, right? So, so essentially what this does is it tells us for a normal distribution with a mean of 50 and a standard deviation of 5, how likely are we to see scores of 50, right? And you can see it's 0.079 or what have you, right? And the exact nature here doesn't really matter that much. What's important is that these numbers are bigger than these numbers, right? Because the further we get from the mean, the fewer and fewer cases we tend to see in a normal distribution, the lower and lower probability of seeing those cases. So very low probability over here, and this is based on like observed data, right? Like if we went and took a big bunch of observations, like 1,000 of them or 1,000,000 of them, we would see a frequency distribution that looks like this, and we can say we don't need the actual frequency. If we have this formula, we know what the probability / frequency / density is because this formula specifies it. So I just want to make sure everybody's clear on what this formula is doing. It's kind of summarizing the frequency you would usually see in normally distributed phenomena, Okay, so if you're clear on frequency and how it relates to probability and that these are probabilities, then we're ready to move on. Okay, so the next thing I did is I went over here and I dug off the internet how to simulate normal data, and you use this norm inverse function or random variable specifying the mean and standard deviation. And essentially what I did is I typed this in here, I hard-coded in what the mean and standard deviation references were with the little dollar marks so they wouldn't change. And I copied it and I pasted it. And I did that all the way down. You can see there's 500 of these guys. So I basically made a sample of 500 cases that follow the normal distribution. So with a mean of 50 and a standard deviation of 5. So most of them should be piled up around the middle, right? That's kind of what we expect from a normal distribution. So this is different than what was over here, right? This over here was using this formula to specify the density of a normal distribution. This is just creating a normal distribution, normally distributed set of values. Okay, so I did something next. I copied and pasted the values over. And if you're familiar with Excel, you know that when you have random stuff like this, you go into the formula and you click return, every single one of these numbers changes every time. So I didn't want that. So what I did is I just took these numbers and I copied them and I hit paste special, and these are the numbers I got. Right? I didn't sort them or anything like that. I just let them raw. But at one point in time, these numbers were the same as those numbers, right? Okay. So yeah, so if you're familiar with Excel, you understand what I did there. So the next step is to actually compute the likelihood, right? So, so the first thing I did first is said, well, you know what? I know that the population parameters, the mean and standard deviation I specified were 50 and 5. And then I said, just for fun, let's just figure out what the average is just by using Excel's average function and figure out the standard deviation using the standard deviation function. And you can see they're awfully close to their population values. Now what we're going to do is we're going to go over and do this with maximum likelihood estimation. Okay, so maximum likelihood estimation will do the following. It'll look at each value right here, and it'll say, if this formula is true, if this data are normally distributed with a mean of 50 and standard deviation of 5, what is the frequency with which we should observe each of these values, right? So it knows this. We're specifying the normal distribution to the maximum likelihood algorithm. And we're saying this distribution follows a normal distribution with a mean of 50 and standard deviation of 5. How likely are we to see a 30? Well, not very likely. How likely are we to see a 50? Quite likely, right? And that's what we're going to do with maximum likelihood estimation. We're going to try different values for the mean of this distribution. We're going to leave the standard deviation the same as 5, the correct value, just to keep it simple. We're going to try different values, and we're going to have it figure out the probability of observing each of these 500 data points. All right, how are we going to do that? I'm going to use this math worksheet thing here, and I'm going to put in the first one we're going to try, 35. So we're going to figure out, what I did is I copied over these data right here, like this column. I copied it, and I pasted it right here, did paste special right here. Okay. And now what I'm going to do is I'm going to compute the probability of seeing a 44.1546. And the way I'm doing that is I'm using that formula that I had over here, because we've already established this is a probability density, right? And what it's going to tell me is if the population mean is 35, what's the likelihood of seeing a 44? And it's going to put that number right there. You can ignore this column for right now. Okay. If the population mean 35, and I just made that up arbitrarily, that's completely just my choice, arbitrary number, right? How likely are we to see a 60? Well, not very likely, right? Okay. Everybody understand what these numbers represent? It's how likely you are to see a number that looks like this if this is the true mean of a normal distribution and these numbers follow a normal distribution. Okay. Okay. All right. So we can do that. We get the probability of witnessing a 44 and a 44.7 and a 39.5. And you can see the probability is higher for a 39 than it is for a 47, right? Because if the mean of the distribution is a 35, right, and the 35 would have a mean centered way over here, it's going to be more likely to see a number closer to the mean, right? So we're going to do that for all 500 cases. And then to compute the likelihood, it's really quite simple. All we have to do is multiply together all those probabilities we just computed. Okay, so it's this number times this number all the way down 500 times over. And the function for that in Excel is product. Okay, can anybody see a pragmatic issue with this? This is fun. I'm going to keep doing this if somebody says something.
0?
It's close. It's not actually zero's the thing, but it's so close, right? It's so close that it's like annoyingly close to see. And why is that? Well, when you multiply together a bunch of little numbers, the numbers keep getting smaller, right? If we only had 5 things here, like if I just did like equals product, right? And then I only did like, let's say we only have 5 things, no problem, right? We just get a small number, but it's no big deal. When you multiply 50, you get a small number. You multiply 500, you get a really small number. And if you multiply 5,000, you get a really small number. That creates 2 pragmatic issues. Number one, before computers, you can imagine people didn't want to carry that many zeros because it's a nightmare. And number 2, even with computers, old computers would literally run out of memory because a computer has to partition a certain amount of memory to hold a given number. And it would run out of memory because you'd have this like 1,000 zeros in front of your numbers that actually matter. And if we went over far enough, like we'd eventually get to some real numbers over here. I don't know how far we'd have to go. I think around, no, I really don't even know. That's as far as it's going to go for me. So yeah, I regret doing that now. I can't get rid of it. Okay, so this turns out to be like so close to 0, we can't actually see what it is, right? So for this reason, people will often take the log of the likelihood. I don't want to get into too much math, but basically you can, if you want to multiply 2 numbers, you can take the log of each of those numbers, add those logs, and then take the antilog, the exponent, and get the real number, get the multiplication number. So it's a way to get the results of multiplication without actually having to do any multiplication. You can take the logs, add all the logs together, and then take the antilog and get the original number that you would have gotten if you've multiplied everything together. Okay. But, so that's what people are doing. People then decided, you know what, let's take the log of this number, and then to get the likelihood, all we got to do is sum instead of multiply. And instead of having a 0 right here, we're going to get a number that we can actually look at and compare to other numbers, right? As it turns out, you don't actually need to take the anti-log of this to get the original 1,000 zeros we had. And in fact, we don't want to, because whatever number maximizes the mean, like the likelihood of the regular numbers, will also maximize the log likelihood. So if 35 were the right mean, then it would be the same for both these, right? The other thing people sometimes do is they take the -2 times the log likelihood, right? Because what you can see here is the original formula, right? If you take the log of it, you don't have a product out here anymore. You have a summation. And then if you take the -2, you can actually pull this part of the formula out of that equation, which is a little bit more parsimonious, right? So what I did here is I took that number over a -2, because that's a lot of times the software will do that. They'll report the -2 log likelihood. And you're scratching your head, wonder why on earth it reports a -2 log likelihood? Well, because it's using normal theory and there's that -1/2 in there. It's pulling that out and it's taking the log to avoid this nonsense you see in this column right here. Okay, so that's why you take the log likelihood and then the -2 log likelihood sometimes when you're doing maximum likelihood estimation. Okay, so back to my point. First off, anybody have any questions before we start actually doing the likelihood estimation? Okay, so this number is the sum of these numbers, and each of these numbers is just the log of that number, and that number came from that distribution that looks like this. It tells you the probability of seeing a 47 if the true mean of the population is 35. Okay. So if this are the true mean of the population, then the likelihood of seeing this pattern of numbers, right, is we can copy and paste into right here. I'm going to paste special whatever, right? Now what I'm going to do is I'm going to try a different number. I'm going to try 40. Well, what if what's the likelihood of seeing these numbers if the mean of this distribution was 40? So again, we're computing the probability of seeing this, but now with a mean of 40 instead of a mean of 35. And you get the same thing. You get a likelihood, a log likelihood, and a -2 log likelihood. I'm going to take those over and I'm going to paste them over here. And take a look at it. This number is getting a little bit bigger because it's a smaller negative numbers, which means it's bigger. And this number is getting a little bit smaller, okay? Okay. So normally what we would be trying to do is we try to find the maximum. We're going to fill in all these numbers here. Let me go ahead and do this, right? So 45, let's go put that in there. 45, copy, paste, okay. 50, copy, paste. $55, copy, paste, and lastly, let's do 60. Now, obviously, I've just made these up. You would normally like try to get a little more precise than what I'm doing here and that kind of thing, but it's a good kind of thought example. So basically what you can see is normally what we would do is we want the maximum likelihood. We would normally look at these numbers right here. We would pick the level of the mean that makes these numbers maximally likely to see, right? Based on multiplying together their probability values. The problem is these are all so tiny, they're all essentially zero. We can't tell the difference. So instead, we're going to maximize the log likelihood. And you can see it's maximized at 50 of these options I gave it, right? The maximum likelihood is 50. And that's what maximum likelihood estimation is. It's drawing this curve and then taking the highest point on that curve. That is that's the value that has the maximum likelihood of generating the observed data of all the options we tried. But yeah, everybody see what we did here. So we maximized, in this case, the log likelihood, and it turns out any number that the log likelihood will also maximize the likelihood. You get the exact same number every time, whether or not you look at this column or this column. And this column, unfortunately, is so small numbers, you can't even look at it. The -2, in that case, what it does by multiplying by -2, you're flipping it. So you actually have to take the minimum here. So sometimes in like the output, you'll see something like the minimum, minimum fit function or whatever, what's being minimized instead of maximized. It's the same thing, right? Whatever case here minimizes the -2 log likelihood will maximize the original likelihood, right? So you can do it either way. These two will always give you the same number. If you pick the highest in this column or the smallest in this column, you get the same exact number over here. And that's maximum likelihood.